Okay, let's look at an example having to do with two tanks that comprise a closed system. So we could see how the second law of thermodynamics for a closed system is applied. So we have two tanks, and I have a sketch here for them. Two tanks, and initially one of them is evacuated. There's nothing here. It's completely vacuumed. I have a valve here, and on the other side, I have 40 grams of some water substance at 15 bars and 280 degrees Celsius. Okay. Then I'm going to open this valve, and I'm going to allow the steam substance to fill the entire container until I reach a second pressure. And this is going to be a mechanical equilibrium. So it's going to be completely equilibrated. There'll be no driving force. I don't know. I know that the final temperature is 440 degrees Celsius, but I don't know this pressure. Okay, so the only thing I know about state 2 is the temperature. I also know that this system is surrounded by air or something at 500 degrees Celsius. And so some heat will be absorbed through the walls of the container and into the system. And it will thereby increase the temperature from 280 to 440. Okay, so what I'm being asked to find in this scenario is the magnitude of Q. I'm being asked to find the final pressure, P2. And I'm also being asked to find the change in entropy from this state to this state, okay, for the system, as well as whatever entropy generation occurred due to the process, okay? So again, as a reminder, delta S is a system type thing. It's due to the system. It's whatever system we're looking at, whether it's a control mass or control volume. And entropy generation is due to a process, okay? All right, so what we know is that this is a closed system. It's the only assumption we can make. We can't make any other assumption. And we also know that the V2 is equal to 2V1. That's kind of like what we were given right off the bat. We don't have any other assumptions to make. We don't know anything. It's not adiabatic. We know it's not, it's probably not going to be an ideal gas. Let's not make that decision to use an ideal gas equation of state. We do know it's a water substance. So it's probably a good idea to use the steam tables, because we know it's got steam in it. Okay, so that's what we're going to do. All I know, and from the beginning, all I know is for state 1, that the initial pressure is 15 bars and that the initial temperature is 280 degrees Celsius. I also know that the mass from state 1 to state 2 does not change and it's stuck at 40 grams. I don't know the final pressure, but I do know the final temperature. So this is just a summary of what we have, as well as this. Okay, so what is the best thing to do first after you establish any sort of assumptions, which we just have closed system, we have nothing else, is to fill out the states so you could use them. Now I'm always redundant with the state being filled out, which is fine. It doesn't cost me much to be redundant. I may use them, I may not use them, the data. Usually I use it. So it's better while I'm in the frame of mind of filling out state variables for a specific state. It's better for me to be over redundant and get them all done at the same time, because otherwise, let's say I needed the enthalpy and I didn't write it down, I would have to go find it again, which I could do. It's just it's gonna waste my time later, and I'm in a different kind of stroke at that point. Okay, so what I'm gonna do, I know this is probably superheated steam. I don't know, probably. So I'm going to go to the superheated steam table, and I know that I have 280 degrees Celsius, 15 bars. So I'm going to go find 15 bars. This is 5 bars, 7 bars. There you go, 15 bars. And I see that there is indeed an entry at 280. So I have the volume, the internal energy, the enthalpy, the entropy. So I'm going to copy all of those down so I have them. These are all specific properties. So I wrote them down for myself here. Here's specific volume. Here's the specific internal energy, specific enthalpy, specific entropy. Again, as a reminder, I put the over bar over S and V just to remind you that these are specific properties. You can tell that this is a lowercase u and h. You cannot tell that this is necessarily a lowercase v or s. Okay, so what I do know and what I apply, this is something that I'm applying from my own knowledge here, that from the statement that of the problem, that the volume doubled. So now I know that the volume here is double that of volume 1. I could not get any information prior because I didn't have two extensive variables being given to me. Now I do. I have the specific volume here. I have the temperature. I have mass. I have enough information to fill out this state. So my first assumption is that this is likely going to be another superheated steam type thing. If it is not going to be in the superheated steam table, I will then go to the saturated water table. So I will first start at, I'll look for temperature of 440, and I'm going to look for specific volume of 0.3254 or so, or ish, or something like that. Okay, so I'm going to go and I'm going to kind of dilly-dally around. And I know that I'm looking for, I know my temperature, so I know it's 440. So if I go here, let's say, I know it's probably not going to be 15 bars. I'm not going to state the same pressure. So let's say I go down to 10 bars. I don't know, whatever. It's right next to it. If I go to 440, hey, look, it's 0.3257. That's pretty darn close to what we wanted. We wanted 0.3254. Close enough in my book. So I'm going to say that now I know my final pressure is 10 bars. And I know my final specific internal energy, specific enthalpy, specific entropy. That's wonderful. And seriously, I just got lucky. It just happened to be the one next to it. If it wasn't, I would have just kept looking for an entry for 440. Let's say this was not 0.3257. I would have continued to look. So I would have seen, for example, if I go here to 7 bars, then at 440, I have 0.46. And at 440 for 5 bars, I have 0.65. So I'm seeing that as I'm going down the pressures, the specific volume keeps going up. And I would have looked for my specific volume that I wanted. I just got lucky that it was the one next to it. So I'm just going to copy all this information over. So part A is complete. I know my P2 is 10 bars. Okay. And then I'm going to fill these out here as well. So I'm going to write everything new that I didn't know that I derived from the table. I guess I should have done this in red too. In red. So I know from the table, this is 10 bars. And that, by the way, answers part 1. I wanted to find pressure. Got it. And then from the steam table, I'm just going to copy down all the other information. I may not need U and H and S, but I'll copy them down. Who cares? So I know my specific internal energy is 3023.6, same units as U1. I know my H2 is 3349.3 kilojoules per kilograms. And I know my specific entropy at the end of the day is 7.5883 kilojoules per kilogram Kelvin. Okay, so I know I got the pressure. That's great. So that was it. Now, that is all I could do for the states. I mean, I can't really think of anything else I would want to derive for these states. So I have all of this. We'll see what I need for anything else. Okay, so let's try to get the delta S for the system. Okay, well, I know my delta S because I know S2 and I know S1. And I know the mass is 40 grams because they wanted the total S, not the specific S. So to find delta S, okay, just do mass times delta S. And this is from the tables, meaning mass times S2 minus S1, okay? And just sub them in. So I know this guy here is 40 grams, and I know these are kilojoules per kilogram per Kelvin. So I'm just going to convert this thing to kilograms. So it's going to be 0.040 kilograms. And I'm going to multiply this by the difference, 7.5883 minus 6.8381. And both of these are in kilojoules per kilogram Kelvin. The kilograms cancel. And I am left with the answer to part 3, which is 0.03 kilojoules per Kelvin. So that, I just kind of skipped part 2 for a sec. That gave me delta S for the system. Okay, I need Q, so I mean I'll get Q. It was just right in front of me, so I jumped into that. I could have done Q first, but I didn't need Q to find delta S, so I just did that. Now I'll remind you, when I'm doing delta S, I'm either doing a delta S for the surroundings or I'm doing delta S for the systems. This for the system. It's specifically for a control mass or control volume that you're looking at. It is not for a process, although you can have a delta S for a process. When we're discussing in these problems, it's usually going to be set to a state between two states, between state 1 and state 2. We're going to look at the entropy generation later as a function of the overall process. All right, so to get Q, what I will do, all that I'll do is use the first law for closed systems. Okay, and so first law, that's probably one of the only assumptions I can make, and not make. I could look at it and see it's a closed system. First law, closed systems, and assume no kinetic energy or potential energy, so it's just delta U. And I get that delta U, okay, is going to be equal to my change in heat minus my change in work. Okay. Now, assume, as another assumption we're making, it wasn't pertinent before, we didn't even mention it, no work. Okay, because you're not deriving any useful work out of this, so you're going to say no work. It's just something expanding inside. That's not doing anything. It's not like it's connected to some sort of rod, or it's not doing anything for you. It's just expanding inside of out of that apparatus. It's not doing anything for us. So we're going to remove the work. So that means that heat is going to be m times the specific value for the heat, Q over m, which is going to be, in this scenario, m times U2 minus U1. So that's cool. We actually retrieved these values up here. And we know that the mass is 0.04 kilograms. So I'm just going to put that in, and that's it. That gives me the heat. So U2 is 3023.6 kilojoule per kilogram minus U1, which is 2748.6 kilojoule per kilogram. So put all of that in, and you get that this is 11.0 kilojoules. Okay. So there you go. We got ourselves the answer to part 2. So 11 kilojoules. This is 10 bars. This is 11 kilojoules. This is 0.03 kilojoules per Kelvin. All that we're left now here is the entropy generation. Okay, so how do we get the entropy generation? Entropy generation, of course, we get from the second law. That's over there in the second law. Second law now for closed systems. Okay. So the entropy balance for a control mass is going to be delta S for the system. Then delta Q, del Q, okay, the heat transfer, divided by the temperature of the reservoir, plus the entropy generation. This is the most general kind of thing for a second law closed system. I didn't make any assumptions. This is what it is. It's always going to be delta S for your system. The heat, due to the heat transfer, divided by the T of the reservoir, plus the entropy generation. Let's go back to that diagram here. That means this Q here is the Q right here at the boundary. So when I'm looking at the boundaries, I'm looking at the Q directly at the red outline, like as it's going in or out, whatever the system happens to be, whatever the process happens to be. I'm looking at the Q at the red-blue boundary right here. And we're going to make an assumption for all questions that the temperature for heat transfer is always going to be the temperature of the reservoir, because this 500 degrees Celsius, the reservoir, the air that's around, we're going to assume it's pretty much constant. Is it? No, it probably went down by like 0.01 of a degree, but it's safe to assume that it's about constant, because basically we have this tiny little apparatus in air or whatever, in a big oven or a big whatever, that the surrounding environment is so much larger that it's okay to make that assumption. And we're gonna make the assumption the heat transfer occurs at the temperature of the surroundings. So what that means, that this is going to be the delta S as we calculated, this 0.03. This is the heat transfer that we just calculated at the boundary. This T of the reservoir is, sorry, 500 degrees Celsius. We have everything and we can solve for that. So that means that the entropy generation is delta S minus, whoops, I integrated already. So just Q over T of the reservoir. And this is 0.03 kilojoule per Kelvin minus 11.0 kilojoules for the heat, as we established, divided by the temperature of the surroundings. And this is Kelvin. And we finally get that this is 0.0158 kilojoule per Kelvin. This is our entropy generation. That's the last bit of it. And the fact that this is greater than 0 signifies that this is an irreversible process. If we were to do the calculation and found out that this was 0, it would have been reversible. If we were to do that calculation and found that this is less than 0, this thing came out negative, that means that the process that we prescribed is impossible.